My name is Kevin Chow, and I'm an electrical engineer.
My name is Spencer Lyon-Gross, and I'm an electrical engineer.
My name is Ilse Morales Duarte, and I'm a systems engineer.
My name is Coulter Ogden, and I'm an electrical engineer and the team lead.
My name is Jesus Suarez, and I'm a mechanical engineer.
My name is Abhishek Sharma, and I'm a system engineer.
Sabino Canyon Recreation Area is an example of the unique beauty of the Sonoran Desert. Every year, over 500,000 people visit Sabino Canyon, purchasing park passes from the National Forest Service. Our team worked with Tucson Electric Power to create a safe, affordable solution to provide the ability to make these purchases without disrupting our desert home. However, what has been designed in the mobile utility connection can be repurposed for any location that can fit our container and needs safe, reliable power in a locale where it is unfeasible to run power lines.
Our performance requirements adhere to the electrical needs of the project, which include the amperage flow, kiosk power needs, battery system, and power loss. Now, since the park has different hours during the summer and winter seasons, the system was designed to ensure that it produces enough power for a minimum output of 2,808 watt across 18 hours during summers and about 1,836 watt hours across 9 hours throughout the winter season.
Our customer constraints focused on the container specs, the voltage range, and keeping the project cost below $4,000. For the container, the team needed to ensure National Electrical Manufacturers Association standards were followed. This included being watertight and sealed from dirt picked up by the wind. TEP required an output voltage of 120 volts of alternating current. Between this, the operating voltages of our equipment, and the National Steady-State Voltage Regulation Standards, there is an overall range of 114 to 125 volts of alternating current. Our physical requirements focused on the dimensions and the setup of the system. Our solar panels are fastened into the roof of the container and therefore are required to fit in less than 8 by 10 feet to account for safe working distance and panel shading. To abide by the National Electric Code, or NEC, the remaining MUC components need to fit within the container and still allow a minimum safe working distance of 3 feet on each side to meet our safety requirements. These requirements include having a DC ground fault protection by way of a chassis mounted grounding lug in compliance with the NEC. In all, our requirements made sure that our system focused on meeting and/or exceeding the wishes of our sponsors.
Our system consists of 2 roof-mounted solar panels, a charge controller, 2 batteries, an inverter, 3 breakers, and a thermostat, all contained inside of a battery box with a door-mounted fan.
We were provided 2 Solon Blue 270 polycrystalline solar panels by TEP. As the name suggests, the panels have a maximum capability of 270 watts of power production individually for a maximum of 540 watts at 100% solar exposure. However, on average, this level of generation is rare. Though these panels were provided free of cost from TEP's surplus stock, thorough research and testing was done to ensure they meet all of our requirements.
We chose a Renogy Rover 60-amp charge controller because of its excellent efficiency in transmitting the power generated by the panels safely to the batteries. It is capable of regulating a maximum input of 800 watts channeled into our 12.8-volt battery bank. It is rated for 149 degrees Fahrenheit, which makes it safe to operate in our container. A thermostat powering a fan is attached to the load terminals to cool the BBA3 battery box.
Our system has 2 lithium ion phosphate batteries with a capacity of 100 amp hours each. With 2 of these batteries, they will provide enough power for the kiosk to be operating on idle for 3 days without being charged. Because these batteries are connected in parallel, they will supply an average of 12.8 volts with capabilities of being discharged up to 70 amps. The lithium crystals in these batteries are protected by an internal battery management system that will activate if the battery is being overcharged, overheated, overdrained, or being short-circuited. Together, 2 of these batteries will last a minimum of 4.5 years due to their high life cycles. Since we live in the desert, the main features on these batteries are the operational temperatures of 140 degrees Fahrenheit. With all these features combined, we designed these batteries into our system to supply any power requirements the kiosk needs.
Solar panels output power through DC current. Since the provided kiosk and most electrical devices run on AC current, it was necessary to find something that would convert the produced power from DC to AC current. The solution to this was the Renogy 700 watt power inverter. This inverter meets all of the system power requirements stated. Additionally, it has an operating temperature range of -4 to 158 degrees Fahrenheit. This inverter is a pure sine wave inverter, which provides a higher level of conversion efficiency and safety for connected devices, versus a modified sine wave inverter, which is only useful for simple electronic devices. It meets a required voltage range of 114 to 125 VAC and comes from an established, industry-trusted brand, ensuring quality and ease of maintenance or replacement by the customer in the future.
A strong pathway to system longevity starts with safety. We used 3 DC circuit breakers positioned around crucial equipment to interrupt the circuit in case of fault currents or other catastrophic events. 2 63-amp breakers were placed around the battery bank to protect the charge controller and inverter, while a 32-amp breaker is protecting the system from the solar panels.
As part of our requirements, the mobility utility connection system was expected to pass a series of 2 mechanical tests. The first test helped to verify that all vital electrical components inside of the system would stay dry in rainy conditions. To simulate this test, a water hose with a measured flow rate of 34.06 liters per minute was used to spray the container for 2 minutes, switching sides roughly every 30 seconds. It was found that there were no leaks and the system stayed dry. The second test related to how well the system resisted the entry of dust. These windy conditions were simulated using a leaf blower with a measured wind speed of 70 miles per hour. The test was conducted for 2 minutes. No dust was found to enter the main BBA battery box, which houses the equipment.
The intent of this test was to find the overall power loss of the system in a specific period of time. Unfortunately, we were unable to complete this test due to unforeseen complications accompanying the recent pandemic. Instead, this test has been replaced through analysis using calculations based on loss coefficients from the datasheets of each respective component.
The solar panel accuracy test was designed to determine if our system is capable of delivering the required watt hours in both summer and winter climate conditions. The system must be able to deliver 2,808 watts over the span of 18 hours in summer months and 1,836 watts over 9 hours during the winter months.
The cooling and heating power output test was created to gauge the power requirements of the kiosk for when it's not in its idle state. These tests were conducted by tweaking the values of the kiosk's thermostat to simulate a climate where the heater and cooler would activate.
After the completion of our testing, and additionally the collection of 24 hours of runtime data recorded by the charge controller, it has been found that every tested and analyzed metric has met or exceeded our requirements. This included the successful enclosure testing, the overall operating temperature of the system, and power output that allows the customer equipment to function year-round. At the end of our senior design experience, we have created a self-contained renewable energy system capable of generating 500 plus watt hours and maintaining the operation of the required customer technology for 3 days on a full charge without any power input. With built-in fault current, heating, and liquid protection, we are excited to provide the National Forest Service with additional safe, reliable power at the Sabino Canyon Recreation Area. Thank you for taking the time today to review our project. We look forward to answering any questions you may have.